I just wanted to go through a quick design of how to design an STM32 F4 breakout board where we expose various interfaces such as I2C, SPI and so forth, and just guide you through how we design that in KiCad, do the schematic, do the layout and the routing, and then also order it via JLCPCB using their manufacturing and also their assembling surfaces. Yes, I just want to show you how to design the crystal oscillator circuit, what kind of external circuitry we still need to get this thing up and running. The main chip I tend to use is the STM32 F405, I believe it's RGT6, and it's fairly fast, up to 170 megahertz. It's relatively inexpensive, I think about €4 at JLCPCB, and enough amount of flash memory and RAM. Okay, so let's get started by opening KiCad. Then create a new project. Let's call it STM32 F4 Breakout. And let's open the schematic. Okay, so luckily, if we click on play symbol, in the KiCad libraries, there is already a part for this chip. So STM32 F405 RGT. Let's just drop that in. Okay, so this will kind of be our centerpiece. Let's put it over here. Other than that, we need a 3.3 volt regulator to step down any input voltage we have, for example 9 volts down to 3.3 volts. So one I tend to use, which is also available at JLCPCB, is the AMS 1117 3.3. It's quite overpowered for this scenario because I think it can deliver up to about an amp of current, which is quite a lot, and our MCU won't be using that much. Okay. So what else do we need? I tend to always put a ferrite bead on the input just to filter any very high frequency noise. I tend to use one which is about 100 ohms at 100 megahertz. So let's just denote that here. Other than that, it's probably pretty good to just use a fuse. We can put that before the ferrite bead. You can choose a value up to about an ampere, but let's, for safety, use a 500 milliamp fuse. So that's just to make sure if there's a short circuit, the fuse blows and you save your circuitry. Another thing which is probably a good practice to do is to use input reverse polarity protection. And you can do that by using a P-channel MOSFET and a Zener diode. But for the sake of time, let's just use a Schottky diode. So if you hook up your power supply the wrong terminals, this will protect it. So let's put that in the front. Actually, let's use the small symbol for that, because we are using small symbols. So Schottky. I tend to always use the small symbols because it saves space. I already know which diode I'm going to be using. It's the B5819W, and that's an amp Schottky diode, 0.6 volt forward drop, and it's available at JLCPCB. So what JLCPCB has, if we just open up the site just briefly, they have this SMT assembly service, and you can see they have a limited amount of parts you can use. So you have kind of all this section here. So if you go into resistors, just circuit and resistors, you'll see they have basic parts which don't cost an extra assembly fee. And okay, maybe resistors will kind of about okay, but here we have extended parts, so that costs about another €3 because they have to change the components on the pick and place machines. So it's always good to try and opt for basic parts when you're choosing components. And I know, because I've done this before, the B5819W is a basic part and it costs us more. Might not be the optimum choice, but for the sake of saving costs, we'll just go with that. Okay, so of course we also need input-output caps at the regulator for stability. And this regulator is stable, according to the datasheet, with 10 microfarads at the input pin and at the output pin. So let's hook them up. Okay, so of course now we need some sort of power flags to indicate what the nets are. So let's add a ground here, connect that up, and an input. So input flag, so it's, again, I'm getting the place power port. So VCC is going to be our input voltage at whatever it could be. This could be 5, this could be 9, this could, I think this regulator goes up to, I don't know, 30 volts, I think, which is, of course, overkill, and this will probably bake this thing, but then we need 3.3 volts of output. Okay, so this is our very simple input regulator circuit. We have a diode for reverse polarity protection, fuse to protect from short circuits, ferrite bead to provide some additional filtering at high frequencies, and our input and output capacitors for stability. I tend to always draw a little, using this place graphic lines, a polygon button on the right here. Just a little box around it, make it look nice and neat, and section off different things on the schematic. So you have to do right click and drawing. And then we can just place text here using this little text symbol here. What do we call it? I don't. Input voltage regulator. How about that? Just put the title here. Okay. Put it over here. Okay. So now we've got our input voltage circuit, voltage regulator circuit. Let's look at our microcontroller. This is kind of the more interesting part. Let me just move the labels around, make it a bit neater. I already know we're going to be using the RGT6 version here, because that's available at JLCPCB. Okay, so since this is a KiCad standard library, it's really quite nicely sectioned. So we have all the VDD, so the positive voltage rail pins up here, the ground pins down here, and sorted into various banks, A, B, and C banks, and various other circuitry. Okay, so looking at the top, the VDD, so let's get our 3.3 volts over here. So VBAT, this pin, if you're not using an external battery supply, which gets activated whenever VDD is missing, you can just tie it up to 3 volts. Because we don't have an external battery supply here, we just tie it to 3.3 volts. If you did have an external battery supply and you would want to switch to that when VDD is not being applied, connect that of course to your V battery. Now VDDA is kind of the analog reference voltage. So if you're using the ADCs in this chip, analog to digital converters, you would probably want to add some extra filtering to the VDDA pin. So because we might be exposing these pins, let's do that. So we derive it from the 3.3 volts supply. Again, let's use the same ferrite bead just for simplicity. But let's add some capacitors, and they're not going to be as large as these 10 microfarad capacitors. I think ST recommends a 100 nanofarad capacitor in parallel with 10 nanofarad, I believe. You can't really go very much wrong. You could do a 1 microfarad and you could do a 100 nanofarad. It doesn't make too much of a difference. Okay, let's just hook these up. And so we're feeding off the 3.3 volt supply, filtering by the ferrite bead and the combination of these capacitors. And then let's place another power flag, 3.3 volts. Let's see, there must be a VA one here. There we go, plus 3.3 volts VA analog. Just indicate this is the kind of analog derived voltage. So we can move that up here. Take this flag and connect it to VDDA. So you notice I kind of always try to separate little sections. So I could go and kind of just, wire this up and connect it to VDA, but your circuit is going to look really messy if you keep on doing that. So I always tend to section things off, use these power flags, and also use, for example, labels, global labels, and so forth. I find it makes the schematic look a lot neater. Okay, so it's looking a bit messy, of course, now because everything's kind of floating about, but we'll group that together later. Okay, so we've done the top part. Let's connect the grounds. So there we go. Awesome. Okay, so ST recommends, and what I tend to do, for every VDD pin available on the chip, use 2 100 nanofarad decoupling capacitors. So let's do that. I don't connect them up to the pins, so I could do this, but that's just going to look messed up if we have about 10 of these capacitors. So I create a whole new section at the top. So how many pins do we have? Okay, so we have 1, 2, 3, 4 VDDs, so 200 microfarads for each of these, and 1 VBAT, where I'm just going to be using 100 nanofarad because we're not actually using this pin. VDDA, as you remember, we've already filtered, so we won't need pins. We won't need capacitors, extra capacitors for that. Okay, so 4 times 2, that's 8. There we go. What's that? 6, 8. I go into 8, and we're using 1 for VBAT. Okay, and ST also recommends placing a larger decoupling capacitor, just, I don't know, about 10 microfarads, close to the package. And let's just use one of these 10 microfarads. Okay, so again, 2 100 nanofarad capacitors for each of the VDD pins. I'm using one 100 nanofarad for the VBAT because that pin isn't really in use. VDDA is already filtered, and 1 larger decoupling capacitor close to the microcontroller package. So now comes the boring part. Feel free to skip this, where I just have to connect these up. So I tend to do the long wire first, and then I can just connect them up like this. So I promise it'll get more interesting after this. Almost there. Okay, of course we can't forget the power flags, 3.3 volts and ground. Okay, just move this over here. So those are all our decoupling capacitors for this microcontroller. Right, and here's our 3.3 volt filtering circuit. Okay, let's just see. This might be a bit closer. Let's move that to the side a bit. There we go. Make it look a bit nicer. Might be OCD, but okay. So now we've got the decoupling capacitors. So this microcontroller also has 2 VCAP pins, and those are for the internal regulators, I believe, inside the chip, and they require low ESR 2.2 microfarad capacitors attached to them. So let's just do that. 2.2 microfarad. So it depends on the chip, all of this, of course, but in general, everything is detailed in the data sheets, and if you follow them and the application notes, you should be safe. So each one of them are 2.2 microfarad capacitors, and you see I am in this case just attaching it directly to these pins because I know on this side there won't be much circuitry and it won't look all convoluted. There are, I think, 4 different boot modes because there are 2 boot pins. There's a boot 0 pin here which is clearly indicated, but PB2, according to the datasheet, also acts as a boot 1 pin. Now the more important one is boot 0 because that, if you tie it low, it's basically in the standard run mode and you can program it via serial wire debug. If you pull this pin high, you can, it goes into DFU mode, it's called. So it's a direct, I think, firmware upgrade, and you can program it via UART or USB. Now it might be a good idea to make this kind of switchable, so either pull it high but pull it low, but in general I think 90% of the time, or even more, I just have this pin pulled down because I program it with serial wire, because the debugging is just so much better. Because of DFU mode, just uploading the firmware wire via UART to USB, you have no insight into the registers and it basically just runs. So let me create labels now just to make it neater. So we have the N reset pin here, which essentially just toggles a reset if there is a low on this pin. So internally this has, I think, about a 40k pull-up resistor to 3.3 volts. So by default this is high, so it's weakly pulled up. And here let's put a boot O label. And just for completeness, I'm going to put the boot 1 label. So this is in the datasheet. Why this PB2 pin is actually boot 1, and this will pull low as well. Not necessary, because essentially this determines the boot mode of the chip primarily. Okay, so what else you'll see in the datasheet is that these 2 pins, PH0 and PH1, are the crystal oscillator pins, and this is the high-speed external crystal oscillator, which is called HSE. We can also open, it's a good idea to download STM32 CubeMX, which I have open here. And this is great for seeing the pin assignments, and I'll show you this here. So if we look for our MCU RG, which is this one, So it's an LKFP64 package, and you can see, look, it's got quite a lot of flash in RAM, and goes up to about 170 megahertz. So double click to open that, wait for it to load, and you can see this is the chip in its default state, and here we can go into different sections and enable different peripherals, and that's exactly what we're going to do. And firstly, let's look at these PH0 and PH1 pins. So you can see this is RCC oscillator in and RCC oscillator out. You can also find this in the system core on the sys, or RCC, sorry. And here's the high-speed clock, and we want to have a crystal ceramic resonator, which will enable these pins when they turn green. So let's just transfer this to the schematic. Let's check, so this was in and out. So HSE in, I'll call this, and I'll call this one HSE out. Okay, so let's place a crystal, because we're gonna, you can use the high-speed internal crystal or oscillator inside, which is an RC-based oscillator, which has, I think, about a 1% accuracy. But if you want accurate timing, you're gonna need a quite precise external oscillator or crystal attached to this. And just for the sake of showing you how to do this, let's do it. Just in CubeMX again, if you go to clock configuration, you can see here's the high-speed external, but by default it's using a high-speed internal, which in this case is a 60 megahertz oscillator. So it's up to you, depending on your timing requirements. You won't strictly need a crystal attached to your device. Okay, but we'll do it. So if you type in crystal into KiCad, you're going to get many different options. So you have a 2-pin crystal, you'll have crystals where there's a ground on the 3rd pin. In general, for these high-speed external oscillators, you're going to want the crystal ground 2 and 4. So pins 1 and 3 are essentially crystal in and out, and 2 and 4 is the case ground. This is what we'll be using as well, because this type of package is available at JLCPCB as a basic part. So let's rename this to HSC, and we're going to be using a 60 megahertz crystal. So as you can, if you go back to CubeMX, you can see the crystal range is from 4 to 26 megahertz. I think 25 is recommended if you're going to be using Ethernet or USB, but I tend to go with 16 because it's a safe bet. But that's entirely up to you and your situation, whatever you need. Okay, so pins 2 and 4 are ground, 1 and 3 are input and output. So I'm just going to move these labels out of the way for a second. Let's move the ground from over here. And then just going to attach the input here, and the output I will attach via a feed resistor, and I'll explain what that is in a second. So R small, put that here, connect that up, and then we have 2 capacitors either side, and these are the load capacitors. And I'll go more into detail how we actually calculate them and why they're needed in a second. So let me just put them over here, connect them all up. Pins 2 and 4 are ground, as we said before. Okay, this is not looking good. I'll just move this to the side a bit so I've got a bit more space. Clean this up a bit more later. Okay, move this to the side. This is looking a tiny bit better. With the label back. Okay, so this is our basic crystal oscillator circuit, which you'll need in probably 99% of the in the scenarios. From the HSE out, we're using a feed resistor into one of the terminals of the crystal, and we have the HSE in, which is basically directly into the crystal oscillator. And we have 2 load capacitors here. So first of all, the feed resistor limits the amount of drive going to and from the crystal. So we don't want to essentially overdrive or distort the crystal waveform, which will produce higher order harmonics. And that's not what we want. So we can limit the drive level by using a small valued resistor. So let's look at how we actually calculate the value of these load capacitors. So let's go back to JLCPCB and see what crystals they have in stock. Let's type in 60 megahertz. And lo and behold, a basic part, crystal oscillator at 60 megahertz. Let's look at the datasheet. Okay, let's have a look. As you can see here, first of all, pads 2 and 4 are ground, 1 and 3 are connected to the crystal, and this is exactly what we have here. Okay, now we need to find out what the load capacitance is. Now, this is a generic datasheet for this line of crystals, and it doesn't really say here, which is a bit annoying. But we know this part is available at LCSC, so let's visit that. Type in the part number, and we see that here the load capacitance is 9 picofarads. Okay, so the load capacitance in total needs to be 9 picofarads. Awesome. So let's go back. How do we know? Do we just use 9 picofarads for these? Well, the thing is then parallel. So parallel capacitors, if they're the same value, which we'll have, so this will be the same value of this capacitor, the capacitance halves if they're in parallel. But we also have to take into account that there will be stray capacitance on the PCB. So this will be the order of about 2 to 4 picofarads. The shorter we keep the traces, the more we watch out with our circuit layout, the less this capacitance will be. But if we assume about 2 picofarads, I'll write out the equation here. So the C load capacitors, let's call it CL, is going to be 2 times C load crystal minus C parasitic, or stray capacitance of the circuit. Right? So this is how you calculate the value for these load capacitors. So the load C load crystal was 9 picofarads. Parasitic is about 2 picofarads. Could be up to 4 picofarads, but let's say 2. So it's 9 is 2 is 7, is 2 is 14. So it's around 40 picofarads, but it could be less. So it could be used 12 picofarads, it could be slightly more, it could be 16 picofarads, but something around that range. For this crystal, I found 12 picofarads works pretty well. So assuming a slightly larger parasitic capacitance. And there we go, that's how you calculate the load capacitors for the crystal. Now the feed resistor isn't always required, and you should be fine without it as well. I just tend to put it in because it's kind of neat. Now, some of these microcontrollers are a bit fussy about the load capacitances or capacitance attached to these high-speed external crystal oscillator pins. Some of them won't allow capacitances maybe above 20 picofarads, and you have to watch out. It depends on the chip, but this one is pretty safe. Okay, so now we've pretty much got all our main external circuitry. Let's have a look. Yeah, we've got all the decoupling capacitors, connected to all the grounds, we've done a crystal oscillator circuit, connected the VCAP pins. Now, let's look at the N reset, boot 0 and boot 1. Remember, we want to pull boot 0 low, and we want to pull boot 1 low. Let's use again a small resistor. And 10 kilo ohms is a sufficiently good value to pull these pins low. So boot 0 and boot 1. Now we could tie them directly to ground, but that means we won't be really able to change the values should we need to, like when the circuit has been made, because here we can essentially just apply 3.3 volts to one side of the resistor and pull boot 0 high that way. But if it's tied directly to ground, we're going to have to cut the copper trace. So it's safer to do it this way. Okay, so for the reset pin, you could use a switch, which is then essentially just tied to ground. So once you press the switch, it ties and reset to ground momentarily and resets the device. Which you can do if you want to do that, but the amount of times you're actually going to have to reset the chip by hand is minimal. The only reason we're going to using it is because it connects to the debug connector. So if we're using JTAG or zero wire debug, the programmer can use the reset pin to perform a hardware reset. Now, let's go back to CubeMX because we want to enable the pins for serial wire debug, and you can find them here. So under sys debug, there's serial wire, and you can see there's the data I/O and the clock pin for SWD, but it is also good practice to include the trace pin, which adds another third pin here, which is SWO, and this allows you to, for example, to print F via the debugger or the programmer, and you can watch variables and plot graphs and so forth. So I tend to always include that pin as well. So let's just see. So that's PA13, PA14, and PB3. So we have SWDIO, we have SW clock, and SWO, which is the trace. So PA13 is SWDIO, PA14 is SW clock, and PB3 is SWO. So PB3 is over here, and that's our debug. So essentially this is our kind of minimal setup, right? We've got the boot pins tied high or low, we've got an external high-speed crystal attached, we have all the decoupling and filtering, and we have the serial wire debug. So you could use JTAG, but I think serial wire debug is fine in pretty much all situations. Okay, now if you have the, I can't remember what it's called, it's the ARM debugger tool, I think ST-Link, that comes with a typical header. It's a 10-pin ARM header. So let's look at the pinout, ARM 10-pin SWD. Okay, and this is the kind of pinout we want. It's the left side. So we have the controller VCC, ground, not connected, ground. Here's the data in IO, clock, SWO, not connected, and reset. So let's use that kind of pinout, because then we can easily attach our debugger just to that header. So let's do that. So place component. So con, it is 2 columns, 5 rows. Now we want the odd even one. This odd even will always translate to this. So it's 1, 2, 3, 4, 5, 6, 7, 8, odd even. So let's use that. And now we just have to wire it up as we see in this picture here. So you have 3.3 volts here, ground, this one, this one, this one. Now not connected, we'll put that here, that's not connected, and this isn't connected. 10 is reset, let's move that over here. SWDIO is the top one, SW clock is that one, and SWO is that one. There we go. And now we've got a connector which has the same pinout as this. It's an SMD mount usually, 1.27mm pitch header, and that will go directly to the ST-Link debugger connector, but we'll pick the parts out later when we do the component assignment. Okay, so now looks like we've got pretty much everything. Let's go back to CubeMX, because now comes maybe the more interesting part. Now we can choose what peripherals you want to expose on this little breakout board. So let's go through. So in connectivity, you'll see you'll have the main interfaces you're probably wanting. I2C, let's draw that. So go to I2C, just click on I2C, and it'll choose 2 free pins. So for example, PV6 and PV7, that's SCA and SDA. Now you can look at the datasheet and have a look around. I2C1 might not just be mapped to PV6 and PV7, so it could be mapped somewhere else. But look at the datasheet for that. But let's just stick with that, just for simplicity. You can also click on pins here and see what functions are available on every pin. That's another way to do it. Okay, yeah, let's go with an SPI, full duplex master. Okay, so we have this clock, MISO and MOSI, and we probably want a chip select. So SPI NSS is chip select. You can just assign essentially a GPIO output because it's just high or low. So let's just do that. Okay, coronavirus. So GPIO output is our chip select. You can also right click and enter user label. So I'll do SPI1 chip select. Makes it look nicer than just saying GPIO output. Okay, so we've got I2C, CL, SDA. Okay, what about a UART? Asynchronous, let's see where it puts it, PA9, PA10. Yep, so we've got TX and RX, and that's, for now we can just stick with that. One thing I tend to do because if you have a UART and you want to use UART for maybe debugging, for example, using printf to some sort of terminal console, you can do that, of course, via UART and then connecting to a UART to USB converter. And that's all fine, but that requires extra parts. You need an extra driver IC and so forth. Now, the nice thing about the STM32s is you also have a USB connection. So if I just do that quickly, so you can use device only, it's PA11, PA12. So that's the it's a differential line, so D minus and data plus. And if you go to middleware, go to USB device, there is a virtual COM port. So you won't need an extra converter between USB and UART. You can just use the UART to, for example, debug. And of course there's many different devices here. You can use a human interface device or a DFU device, audio, and so forth. So that's just a little tip. If you want to save an extra chip, which can be an extra cost, of course, if you do this in volume, just use the USB and use virtual COM port. But for simplicity for this one, I won't be doing that, because then you have to route differential lines with a USB connection, and for the sake of this video, I'll just keep it short. Okay, but our connections are I2C, SPI, and one UART. Okay, so let's just have this next to each other. So, PB6 and PB7. That's I2C1 SDA is PB7. And I2C1 SCL is PB6. Okay, UART is PA9, PA10, so UART1 TX is PA9, and PA10 is UART1 RX. Okay, and finally we have SPI, which is a PA4, PA5, so they're all in this kind of bank. So SP1, chip select, just making loads of labels and just labeling what all these pins are. And this is good because later, when if should things go wrong, which they might, you can see immediately that it's SPA1 and what pins they are, without then, for example, drawing huge wires to some part of the circuit and you don't know what the hell's going on. This is the way I recommend doing it. PA6 and PA7 is MOSI. Okay. Now, what I tend to include as well is an LED just to show the status, that if it's running. So you can have an LED, for example, blink with a frequency of 1 hertz, so once every second, just to show that the thing's running. So if the simplest checks are often the best, so let's do LED and connect that to essentially almost any free pin. So you have to watch out because some of the pins don't have the current drive capability. So check with the datasheet. Most pins should be fine, but some aren't. Okay, so an LED, let's say we want the red LED here. Take a resistor, so you could work out what current you want just by knowing the forward voltage drop, which is about 1.8 volts for a red LED, figuring out what current you want to go through it for what brightness. But a fairly low brightness, you'll be fine with a 2.2K resistor connected to, I don't know, PB12, where's PB12? Yeah, it's here. So we can just say this is an output. And to use the label, this is LED status. For example, it doesn't have to be. I mean, you can of course omit this LED, but I think it's a nice thing to have. I think Arduino has it as well, where they have like a status pin that flashes and you can use. Okay, but the remaining pins we're not going to be using. And in KiCad it's a good idea to use this no connection flag to suppress warnings. So let's do that. This is a bit boring. Okay, on to this side, using these no connect symbols. Oops. And on this side, feel free to fast forward this bit as well. Almost done. Okay, so now we've pretty much got everything hooked up. SPI, UART, serial wire debug, the boot pins, the reset pins, the crystal, caps, SCL, I'm just checking everything. And of course you want to take your time when checking the circuit just to make sure everything's correct, because you can waste a lot of money redoing circuits, especially with the PCBs. Okay, one thing on the topic of LEDs, let's add an LED here, just to indicate that the power's on. For prototype boards, it's always a good idea to do this. Other LED, why not? You could use a green or blue, but of course that changes the forward voltage. But let's just make things simple. Click LED, go. Okay. Now, we can now group this microcontroller. Let's put a little box around it, just make it neat. So let me just rearrange. Now this is just the way I tend to do it. This is by no means the only correct way of doing it, but my boards have worked so far, and I just wanted to, because I haven't seen videos that explain this kind of in this way, how to just do a simple hardware design which follows the datasheet guidelines. So hopefully this will help some of you out there. Let's move over here. Sorry, this is taking a bit longer. Okay, this will do for now. Let's draw a little box around it to section the circuit. There we go. Very rough, but you should do. End drawing. Put a label. Let's just call it microcontroller. Okay. Now, you might have noticed that I didn't group this connector with the microcontroller section here. Well, that's because we need to add connectors for everything. So we need to add a power connector for the voltage input, we need connectors for the SPI, for what else we have? UART, of course, and I2C. So let's do that now. And I tend to just use these generic connectors. So here's a 2-pin connector. We can connect UART, and we can connect the TX and RX lines. We can do the same for I2C and SDA. Now on the topic of I2C, something I forgot, which is pull-up resistors. So you can either have the pull-up resistors on the board, which is what I recommend, or off the board, something else, but you're always going to need pull-up resistors on the lines. So let's add those. So the higher your speed is for I2C, the lower the value of the pull-up resistor needs to be. For most cases, a safe bet is just using 2.2 kilo ohm resistors. So this will enable you to go fast mode with I2C, and also, I know, the normal mode at 100 kilohertz. What you'll be noticing as well is, I try to, so any power flags that are positive, so plus 3.3 volts, I tend to have facing upwards, and anything low voltage like ground or negative supply rails, I have facing downwards. So here, boot 0 is going this direction, and anything that's pulled up is actually, moving up. It's easier to read, I find, and you can kind of stay consistent. Okay, so that's the I2C pull-up resistors, and finally we have the SPI, so that's a 4-pin connector. And just copy the labels. Okay, now we need one more power, which is just connected to VCC and ground. Okay. Now what I tend to do as well, I tend to have at least one header where I actually expose the 3.3 volt rail. So this could be to power external circuitry or just as a test point to see if there's what voltage it's actually at. Because the LED will indicate that there's some voltage there, if there is, but it won't tell you, of course, what the actual voltage is. And you can read this with a multimeter much easier. So just roughly group them. So this won't be the prettiest schematic, but the basic idea is group everything, put it into the sections. Makes it much easier to debug and read. A little box around it. And let's call this connectors. Awesome. Okay, so one more thing which you need to do in the schematic, if you want to, of course, is add mounting holes, and you need to do this in the schematic layout editor. which I still find a bit weird, but anyway. Place symbol, mounting hole. I tend to do it with the pad because I tend to ground my mounting holes. Because if I want to connect this to, for example, a metal enclosure, it will provide a nice Faraday cage. So I tend to ground them, 4 of them, because we'll have 4 corners. Connect that up. Okay. There we go. And draw. Again, text. Now, let me make this a bit neater. Okay, so now you can see we've got all these different sections of the schematic. We have the input voltage regulator, input voltage protection, fuse, filtering, just checking everything, all the connectors, debug connector, power in, power out, and so forth, mounting holes, and of course the main microcontroller circuit. Okay, this seems to look alright at the first glance. Now, the next thing we need to do is annotate the components. Annotate means essentially assign numbers to individual components. So we're going to have, I don't know, about 20, 30 capacitors, 20 maybe. So it will be C1, C2, C3, C4, C5, C7. So you could do this manually by just, double clicking C1, C2, and it's a bit tedious. You can do this if you want, but of course this will take a while. Now KiCad has a feature built in where you don't have to do that manually. Okay, more coronavirus. Click on Annotate up here, and there are several options here. The most important one for me is essentially how you want them sorted by. So essentially KiCad will go through and say whatever's left gets leftmost gets annotated first. So it'll be D1, then it'll be D2, it'll look for the next diode, which is starting on the left, so it'll kind of scan like this. But you can also scan kind of top to bottom. Depends on how you've layouted, how you've done the layout of the circuit. Let's just do sort by Y position. See what it does here. Click Annotate. So we've done that. It's done all the connectors. See, it's done left first before it does the vertical position. But this looks right? It's on C through to 12. This seems kind of logical how it's annotated. It's sometimes a bit annoying. If you have, for example, capacitors which maybe are up here, it'll annotate them annoyingly, and sometimes I have to do it by hand. But in most cases it works fine. Okay, so now we've labelled everything. Everything's looking good. We can now do electrical rules check. So click on the little ladybug, click run, and there's going to be some things which are wrong. Or maybe it just gives us warnings and says this doesn't look quite right. You can go to the options and select what kind of errors and warnings you want it to throw. Generally, unspecified pins, you can get rid of all the warnings because unspecified and specified, as long as you look through it properly, it shouldn't be a problem. But let's go through. So you can click on them one by one. Connect to the pins not driven, it's fine. Yes, it's complaining. Everything's fine. The ones you have to watch out for are errors, so not warnings. Errors are the ones which will probably get you if something is. It's great for checking if things are actually connected. So if you there's a pin which has a flag, maybe, I don't know, 5 volts, but it can't find the 5 volt flag anywhere else. That means it's probably disconnected. So it's always a good idea to do that. So first of all, annotate, and then perform the electrical rules check. Okay, but this seems to be looking okay. I recommend going through it thoroughly again, printing this out on paper, the schematic, checking the data sheets, checking that everything's right. This is a fairly simple board, so this should be fine. But honestly, you will save so much money and time and bother just going through it, just spending an extra day, sleep over it and check it the next day. This is talking from experience. Okay, next thing we need to do is of course choose the footprints for the different components. And let's do that by clicking this little button, Assign PCB Footprints. So it'll take a little while to load. And we will do this in conjunction with the JLCPCB kind of inventory, because we want to choose parts that are basic parts, not extended parts, so we don't have to pay extra. And of course we want parts that they have in stock. So, I don't know, so deselect that, kind of stretch this out. Okay. My general rule of thumb is the larger the value of capacitance you want a larger footprint? This is because also the voltage rating of the capacitor will be higher, and generally you want to maximize the voltage rating of the capacitor. Even if you know there are only going to be 3 volts across the capacitor, choose the one with the highest voltage rating. So 10 microfarad capacitor, let's type that in, JLCPCB, and we get several options, which are basic parts, and this is what we want to be looking at. Extended parts cost more. To change, you can only have up to 10 extended parts on 10 different extended parts on the PCB. So let's stick to basic parts. Let's have a look. So we have an 0805, it's very large, 25 volt rating. What else do we have? See, there's a 6.3 volt rating, that isn't good, because especially these, C1 for example, will be at the input here, and who knows what voltage will be applied here. So if we put a 6.3 volt capacitor here, that might blow up. We also have tantalum. Wouldn't recommend that initially, so let's have a look. So yeah, so it looks like 0805 is the best choice. It's about 25 volt rated, let's choose that, and it's large input capacitor. So double click 0805 here, SMD 0805. So we have 2, which is the output. Let's keep that the same as well, 0805. Now C3, remember, is this large decoupling capacitor for the microcontroller. And the voltage here is only 3.3 volts, so we won't need that kind of voltage rating. So there's 042, let's go with the 0603 one. It's larger than 042, and it has a better voltage range. So all the 100 nanofarad capacitors, so these are all the decoupling capacitors here, those I always go with 042. So 042, if we type them here, 6.3 volts, that's fine, we're only running at 3.3 volts, whoops, and of course it would help to type in the proper rating. There we go, 60 volts, even better. 042, it's in stock, they have got millions in stock, and they're incredibly cheap. So 042 was tend what I go to, because they fit nicely at the pins. So just 042, all of these. So 10 nanofarad, that's for the VDDA pin. Remember here, so 10 nanofarad. 50 volt rating, perfect, 042. So you see what I'm doing, I've got this window open here where I should choose the part. I have the JLCPCB window open to see what parts they have in stock, which parts are cheap enough, and they have the right voltage rating, the right size, and I also have a schematic to check, okay, where in the circuit is the part? What voltages do they need to withstand, and how big do they need to be? So 2.2 microfarad, remember these were these VCAP pins, and they said low ESR in the data sheets, you want low equivalent series resistance. Now, if we type in 2.2 50603, these are the ones I tend to go for. They're not exactly lower ESR, but I have had no problems so far with them. So, but generally watch out for these things. So 603, these two, 12 picofarads, those were these 2 load capacitors here, and type in 12 picofarads, I want an 042 size, it's a basic part. Good voltage rating, yep, perfect, 042. Remember, 042 you can still hand solder, but since we'll be using the JLCPCB assembly service, you know, might as well go as small as is kind of feasible, possible. Some parts you might want larger, right? So some parts which you might want to change yourself, for example these pull-up or pull-down resistors, or these ones here, you might want to make larger, because you can desolder them better, you can get to the pads, they're bigger pads, you can change the voltage and so forth. Okay, so remember I said B581W is a basic part, it's a Schottky diode, and the package, which is important for this one, is SOD123. So let's go SMD, SOD123, perfect, it's a KiCad footprint. So for the ADs, just type in AD, and I'd like an 0603 size. And we wanted red, which is here. So this is the part number, package, okay, 0603, they have it in stock, let's see. 0603, SMD, perfect. Now fuses is a bit annoying with JLCPCB. They only have them as extended parts, which is a bit frustrating because fuses you pretty much need, well, in almost every design. So hopefully one day there'll be basic parts. But here you can see the different sizes, 1206, 1812. What I tend to do, I have a whole stack of fuses at home. So instead of paying €3 every time I need to order a board with a fuse, I just solder them on myself. So I'll just choose something which I have in stock at my home, and then I'll just solder that on myself. So fuse, I think I have 0603 at home, so I'll just choose that. So that's potentially what to do. So if there's extended parts I can easily solder myself, I'll just do it myself because it's not worth paying extra €3. So I'll type in bead. So they only have 2 farad beads. There's one which is 100 ohms at 100 megahertz, and there's one which is 600 ohms at 100 megahertz. I tend to go for this one, which is an 0805 size. 0805, 0805. So mounting holes. Remember we put this on the schematic here. You can choose anything you want here, pretty much. I tend to go for larger M4 pads with the vias. They look cool, I think. So look at the footprint. You see it's this kind of shape. It's an M4 size hole, but it's got loads of vias around it. Choose those. Now 16 megahertz crystal. Type that into JLCPCB. As before, there's this one basic part. The important thing is now the package. So it's an STM32 4-pin, and amazingly, we've got this already in our KiCad library. So 3225 4-pin. There we go. Okay, next thing are the connectors. So connectors here. What I tend to go for, and well, for circuits which are basically just for like prototyping and breadboarding, I go for 2.54mm pitch headers, and these are the standard GPIO headers you'll find on Arduinos, on Raspberry Pis and so forth, and you've probably got loads of cables lying around for them. So that's what I tend to use, and that's what we're using here. So just, where are they? Pin headers is what we want, 2.54mm vertical. Perfect, that's what we want. I'll just add them to this as well. Pin header, vertical, and the last pin header, vertical. Okay, so J4 is this one, and that's the serial wire debug connector. And this, as I said before, connects to the ST-Link for debugging, and it's a standard 1.27mm SMD mount. So this is where you have to pay a bit of attention. It's 1.27mm pitch, and it's vertical, and it's SMD, which is what we want. Awesome. Okay, now finally we're coming to the resistors. Now resistors, again, it depends. If you want to change them later, go for a larger size. If you think you're going to fix them, go for the smallest size which is possible, plus watch out for the power rating. So for the LEDs, calculate what current will be going through them, the value of the resistance, and you work out what power will be dissipated in that resistor. For LED resistors, so for example, the ones we have here, R1, which is 2.2K, and R7, because of the large value of resistance and the low voltage, there's not going to be much power dissipated in them. But for good practice, I choose a larger resistor for LEDs. So I'll choose 0603 for the 2.2Ks. And now that was R1 and R7. Now, always a good idea to check 2.2K if they have them in stock, which they do. And it's a 1/10 of a watt, which is fine, plus minus 1% of resistors, 603, perfect. Okay. Now for all other resistors, for example these pull up and pull down, you can make them larger of course, but it's nice to have small resistors, so I go for 042. And you can be pretty sure that standard values like 2.2K or 10K will always be in stock. But for the sake of principle, 10K, 042, look, they've even got two, one of them is plus minus 1%, one of them is plus minus 5%. Yeah, and that's fine. And I'll have 2.2K in stock as well. And finally, the crystal oscillator feed resistor, they have in stock as well. Awesome. You'll see for the standard component packages they have here, so this regulator and this STM32, KiCad has already filled out what packages they are. So, apply, save schematic and continue. Let's just check just make sure they really have this in stock. So AMS117 3.3, as we see, they have loads in stock. It's very cheap, and it's a basic part, which means you don't have to pay extra. And you see it's up to 800 milliamps at 1.3 volts, so it's 1 amp at 3.3 volts, so that's plenty. I mean, it's overkill, but okay. And finally, let's just check that they have this microcontroller in stock, 405, and there we go, exactly the one I chose, 405 RGT6, and it's about €4, and it's a basic part, which is great. Awesome. Okay, and that concludes assigning all the footprints to all the parts. Now the next thing you do is generate the netlist, because then we'll be moving over to layout and routing. Just save it in the folder. Awesome. Okay, let's move on to layout. Okay, so now we're ready to lay out the PCB, and we go up here to start PCB new, and we're presented with this blank canvas. So we're going to be laying out a 4-layer PCB. Generally, anything with a microcontroller or high-speed crystals and high-speed traces, you want to go with at least a 4-layer PCB. 4-layer PCB is sufficient for most hobbyist kind of electronics, and nowadays it's so incredibly cheap, there's hardly a reason not to do it. If we go to JLCPCB, as you can see, I've typed in 4 layers, and anything up to 50 by 50 millimeters is only €12. Plus shipping, of course, but that's been incredible. If you go just a tiny bit above, it'll double the price, so that's why I tend to go with 50 by 50 millimeters. And we'll go through all the settings once we finish the PCB. But yeah, okay, so 50 by 50 millimeter board. So I'll do that before I import the components. Now you can import the component or the netlist first, and then see what kind of size you might be needing. Of course, you might need more than 50 by 50 millimeters. In many cases, you will. Sometimes you'll have constraints of what the shape of your board needs to be, what the size of the board needs to be. But for now, 50 by 50 millimeters should be okay. So we go to the edge cuts layer, click on add graphic lines. Spacebar resets this kind of counter or this measurement tool at the bottom, and this is how I generally get my sizes. So click, left click, and then look at the bottom right until we reach 50 millimeters, which is here. Spacebar again, reset, click, and go down, again 50 millimeters. And we do this for the 4 corners, and we can just join this up here. Okay. Amazing. So if we go to View, 3D Viewer, amazingly enough, we've got a 50 by 50 millimeter board. Now I will import the netlist. Going up here, load netlist. You can choose your net file, and then click Update PCB, and there we go. All our components are here and ready to be placed. As you can see, we could have made probably a smaller board, because this looks like it will fit easily into 50 by 50 millimeters. But if you can, make the PCB a bit bigger, makes it easier to solder, makes it easier to probe with an oscilloscope or multimeter, whatever. So yeah, let's get started. I tend to turn off this FFab and BFab layers, because there's fabrication layers which have, for example, the footprint names and designators. Makes things easier to see. So let's start with the mounting holes. Click on the first one, press M, and it'll move. And I try to line it up here. So here it's snapped quite nicely to the grid that have a bit of space, a bit of clearance up here, and have a bit of clearance to the left of it. And that's generally what I try to go for. You don't want to mount pads directly at the edge. The board manufacturer will have specifications or design guidelines of what distances and minimum distances you need, but this seems about safe. I prefer to not have these kind of designators on the Silkscreen. I don't think it looks very nice, and I tend to add my own designators. And I tend to, when I assemble it myself, I tend to just have KiCad open and do it in parallel. Also, these aren't necessary for the assembly with JLCPCB. You send them an extra footprint positioning file, so you won't need these, to me, quite ugly designators. So what I do is double click on the footprint text and move it to the fabrication layer. So they're still there if you need it. So if you click FFab, you can see the designator. So that's how I do it. Okay, so let's just go through all these. You'll see they'll align nicely. FFab, It gets a bit tedious moving these, but you know. Okay, so there's a reason why I'm doing the through holes, the mounting holes first. Firstly, because it'll kind of give me an indication where I can place the remaining footprints, because I want mounting holes. I generally always think it's a nice idea to have mounting holes. And I mean, if I look at a 3D view now, right? I mean, it looks pretty cool, but what we want is rounded edges. Rounded edges give you such a much nicer look, I find. And we can do that very easily. I tend to move these mounting hole footprints here first, so I have a nice reference of where my roundness should start, so to speak. So again, we're still in the edge cut layer. We're adding a graphic arc. We're going to the center of the footprint. Click, drag out to the edge of the board. Click again, and we want to go anti-clockwise, because if we go clockwise, it'll start making essentially a whole circle and subtracting from that. So we want to go anti-clockwise, and we want to go 90 degrees. So we do that for all sides. Click, center, anti-clockwise, and let's do that for all 4 corners. Okay. Last one. Okay, now we need to get rid of this kind of overshoot. So we click on one of the edge lines and just drag out one of the endpoints until it hits the kind of quarter circle. And we do that for all sides. So we click and drag, click and drag. Not long to go now. Click and drag. And the last one, getting a bit bored of this. And they're nicely joined up. If we click View, 3D View, we have, a bit hard to see with a dark background, but we have nicely rounded corners with a nice separation between the pad and the edge of the board. And I always think that looks pretty cool. Okay, so next thing we have to think about is how do we want to lay out these components? We always want to make essentially the traces between everything as short as possible. So all the connections that need to be, we want to make the connections as short as possible. Of course, if that isn't possible, try to prioritize traces. So something like SPI, which works at a couple, I don't know, is it 10 megahertz, maybe a bit faster. Make those shorter than, for example, the UART lines, because UART lines will be significantly slower, usually. Things like that, or LED connections or power connections. Minimize the trace length in general, but prioritize, of course, the more important traces. Also, in terms of trace thickness, try to go for the thickest traces possible, especially for power lines. It aids with heat dissipation and makes sure the voltage drops across longer runs of traces are smaller, and so forth. Okay, but let's start with the centerpiece, which is our microcontroller, U2. Now I tend to move that into the center of the board because it looks nice, so here's my reference point. I press space to align, and then we want to move 25 millimeters in this direction and 25 millimeters down. And this should be central. Right? Again, get rid of this reference designator. Okay, what else do we need? Next thing, so I've moved the microcontroller first because this is our centerpiece. Now if you look at the schematic, we want to route the most important traces first. And to me, the most important traces are the decoupling capacitors. We want them as close as possible to the 3 volt or the VDD and VSS pins. The VCAP pins are very important, that they're close, the capacitors. And of course the crystal oscillators might be one of the most important things, right? So let's start with the crystal oscillator, which is C17, C18, R6, and of course the crystal. So what you can do is put them next to each other, and if you click on one component in the schematic editor, it'll automatically snap to that in this right window, which is very useful. So that's what I tend to do. I have 2 screens, but I'm doing it on one now. So I move it in the general vicinity, get rid of the reference designator. So I move everything kind of roughly first, and then I change my grid and move it more precisely. So crystal, roughly, let's see, oops, that didn't. So somewhere here, and the orientation is kind of this orientation. Remember, this is just a rough placement. Now the load capacitors, this one needs to go on this side. remove the designator. The other one needs to go on the other side. Remove the designator. Okay. Now, that's the crystal oscillator parts placed very approximately. Now, what about the decoupling? So let's start with the smaller ones first. It's 100 nanofarads. Remember the bulk 10 microfarad is close to the MCU but not very close to the pins. So pin 1 is here, and that's the VBAT pin, and that only gets 100 nanofarad capacitor. Then we want pin 19, should be somewhere down here. You'll see the 3.3 volt and the ground pins are very close together, and exactly for that reason, so you can put the capacitor essentially right in the center, line it right at the center of those two pins. Remember, we want 2 of these here. So this is the usual way I go. Just rough placement first, get rid of these annoying reference designators. I find it annoying, you of course feel free to put them down. Start with the most important parts first, crystal oscillator, the centerpiece of the board, which is the microcontroller. Then the decoupling capacitors. So this, I'm going through it quite speedily because I don't want the video to be too long, of course. So bear with me just placing these. So I've constantly got an eye on the schematic where the pins are. C10, we're almost there. Amazing. Whoops. Fab. And the last 2 are going to go here. Remember, rough placement. It'll look a lot neater when we're done. But it's also a good idea because if you do a rough placement first, you can kind of gauge if things are going to fit or not. If you need to make the board bigger, if you need to rearrange components, instead of going in directly and fidgeting with the very small grid sizes and trying to get it nicely, things are bound to mess the component placement up. So just do kind of a general rough layout first. Of course, in the case of this board, we didn't have very much on it, and it's a fairly large size board for what we have on it. So, you know, it doesn't matter too much. Okay, next thing we have the analog VDDA supply. We want the smaller capacitor, so we have 100 nanofarad and 100 nano. I just realized I've put NF behind everything. Yeah, ignore that. So we always want essentially 100 because the units are obvious if we're using capacitors or resistors. I messed up there. Okay, but anyway, we want the smaller capacitor smaller decoupling capacitor closer to the pin. So if we have a 10 nanofarad, 100 nanofarad, we want the 10 nanofarad closer. Alright, so we place C14 first because it's smaller and closer, and then we place C13. And we also have a ferrite bead. Now, because JLCPCB only has 0805, this is going to look incredibly large, which is a bit annoying, but it's just aesthetics. Okay, so then we also have the VCAP pins, which are also equally important. And the rat's nest will tell us where it needs to be placed. And you can already see here, we're going to have to move some of these capacitors around. So maybe here, so we have space for this VCAP capacitor. And same thing over here. There we go. Again, rough placement. So it might be a bit annoying with this split screen, but don't worry, once I've done the rough placement, we'll just move over to completely to PCB new. And then we have one large decoupling capacitor, which we can just put somewhere close to the MCU. Okay, now of course we have other circuitry, for example, pull up and pull down resistors, but they don't have to be close or too close to the microcontroller. For example, the boot 0 and boot 1 pins, as long as they're pulled high or low, it doesn't really matter how far away they are. So the same goes for the AD, except for like power losses, of course, but they're going to be minimal across this size of board. So what we can do now is actually do a bit more of a finer placement. So I'll change the grid, and I'll start with the crystal oscillator. So you can see the N reset pin here is right next to the oscillator out, but I'm prioritizing the crystal oscillator. So that's why I can block this pin, because I can just use a via and go off to the debug connector. So prioritize the more important things. And kind of for the crystal oscillator, you want to minimize the trace lengths. Okay, I want to see this is going to come out like this, so maybe move it up a bit. There we go, so I have a nice straight connection here. There, let's put this central and fairly close. These are the load capacitors. I'm just making sure everything's aligned nicely, nice and symmetrical, and this looks pretty good. Okay, here, let's get them very close and central. You see here, if I press M, I get these guidelines of where the center is of the component. And this is so I can take out the traces very nice and symmetrically. Okay, this is the larger decoupling capacitor, and this is the ferro bead, which I can just put somewhere around here. Now, if you're hand soldering this, you might want to leave a bit more space between the components, because this can be very fidgety if you're hand soldering this. But since a machine will be doing this, we can be very liberal with our placement in how close we are. So, same thing here. Now you notice these distances here, you can go ahead and measure, you know, this is 0.2 millimeters, is this the same? Let's be honest, it looks huge here, but if you actually zoom out, this will probably be the real size of the board, or something like this. So it's purely aesthetic. If we go to view, we can see how the component placement will be. And this looks, you know, you want to make it look nice, and this is sufficiently close to the pins. Couple millimeters max. If possible, as close as possible, you want these decoupling capacitors to be. So this is V cap. Let's put it somewhere here. Decoupling capacitors. The second V cap. Now this one I'm going to move slightly up, because this is the SWDIO trace right below it. This is more important, for example, than the end reset. End reset is just high or low, and it doesn't change very often. SWDIO changes a fair bit at a high frequency, and we don't want to use vias too much around high frequency traces, because that'll add inductance to the line. And of course, inductance isn't, well, AC isn't a fan of inductors. Okay. Alright, decoupling capacitors. This is kind of the last set here. This looks, oops, this looks good. I will rotate this. Large decoupling capacitor here, this is the bulk decoupling. Now the reason I rotated this decoupling capacitor, this is the VBAT pin, which isn't very important because it's just turned to 3.3 volts and it won't really be used. And we only have one capacitor. The reason is I want as much clearance around this crystal oscillator as possible, because this is going to have its own ground plane attached at only one single point, and I'll show you how to do that in just a second. But this component placement looks pretty good. Okay, let's change our grid to a larger size again and continue with the rest of the placement. So this is basically the MCU side almost done. What is left is, of course, these boot 0 and boot 1 pull up and pull down resistors. Should be somewhere here. Okay, Tokyo Olympics postponed. Again here, boot 0, I can just squeeze that in here because I have got the SDA and SCL lines right next to it. So I don't want, for example, to put it somewhere around here because I'll just block these pins. So always be aware of that. Just kind of a forethought. You can do everything in the moment, but you're going to probably have to change it in the future. So put that here. And then pull up resistors. Let's do that later because they can be next to the output pins as well. So change the grid. Should do. Okay, looks cool. Yeah, okay. I always tend to go back to the 3D view just to see, is it too close? It's kind of a, I feel like I can see it better if I go through the 3D view. Plus it looks kind of cool. Okay, so this is the first layout for the MCU. What else do we have? Okay, we're still missing these pull-up resistors. And another section, that's why we've sectioned it, is the input section, input voltage section. Well, let's do that next. So I'm just going to move some parts out of the way. So we have the regulator. Let's say we can put that somewhere up here. doesn't matter for now. We have the input and output bypass of decoupling capacitors. And again, you want them as close as possible to the relevant power pins. Ground pins not as important, because the ground pins we're gonna have this huge copper pole as one of the layers and connect via vias down to that. So input and output decoupling. So again, as close as possible. Perfect. Okay, ferrite bead going into the input for filtering. And of course, okay, this is my OCD kicking in because I want every line to be straight. That's nice, okay. Of course you don't have to do it this fine. I mean 0.01mm grid, that's, you won't be able to see it. Okay, we have the fuse, which I'll just move over here. Fuse, and of course we have the reverse polarity protection diode. So you'll see I often juggle the components around a bit, it's always an active process trying to get a kind of optimal layout. I thought something is this, and this will work in many different configurations. But okay, awesome. Get rid of the Silkscreen here, and we can already put down our input connector. We can leave the power connection up here. That seems alright. Okay, get rid of the Silkscreen. Now, connectors, I always tend to put a fixed distance away from the board edge, so it looks nice and even around the whole board, but we'll do that later in time. You can also see I've put the regulator fairly close to the microcontroller, so the power doesn't essentially have to travel a long distance. I could put the microcontroller completely up here, and the regulator completely down here, but that'll cause long, traces and distances between parts. So there's a bit of thought to this. Okay. Next up, okay, indicator diode, that's not important. We can do that fairly close to the end. Okay, what about these other headers and connectors here? So where is, okay, so UART is on this side, so let's put the connector on this side. Somewhere around here. And you see I rotated the connector so that there's not going to be any crossing air wires, because then you'll have to use wires, and that's completely ridiculous because we have very straight connections here. What about SPI? And remember, you can always go back into the schematic if you're not happy with the assignment of the pins of the connectors. You can always change that and then click this button up here, update PCB from schematic. It's always an option. Okay, but here, here I can already see I might have forgotten about this chip select pin, so I'm going to move these decoupling capacitors a bit more to the right, so I can lead out this chip select pin much easier. And these traces will still reach, and still be a small enough distance. Okay. What else do we have? I2C. So I2C, I will move up here as well. And you see how I'm aligning it? I'm just lining it like this, right next to the other connector, which I know which is in a good place. And then if I press M again, I can see these little guidelines, which will help me place it along the same height. And I'll put it somewhere here. You don't want to put it too close to these mounting holes either. Okay, and what this means, because we put down our SCO and SDA connections, actually they're crossed over, aren't they? See, here's a case where I would change something in the schematic. Because of, well, purely aesthetic reasons, you always have this one indicate, on the Silkscreen, this one indicator here, this little right angle. And I want that always facing up, so to speak. But here, if I want it facing up, these wires will cross over. So what I can do in the schematic is just flip them around. So go here, move, flip them around, and then press update through PCB, and there we go. It's facing the right way, and they are Oh, I'm not crossing, and it's the right way up. Same thing here, right? I actually want this to be like that, and I'll do the same thing here. Update PCB, and I have a feeling the SPI might be a bit of a pain as well. Yes. I mean, all facing. Yeah, I could do that, could do that. I could have just changed this to be the other way around, to be honest. That would have been much faster, but, you know. Okay. Just eyeballing the distance here. It's about a millimeter. It's about a millimeter. I'll just flip these around. There we go. Okay, now everything's satisfied my OCD. And now I can just fix this distance. It's being significantly higher. So what was it, 0.95 about? So 1, 2, 3. Okay, there we go. As a fairly rough layout, it should be okay. Now, one thing which is bothering me a bit is this I2C lines will have to cover quite a large distance. So what I'm thinking is I'm going to move the regulator. Whoops, I hate when it doesn't. Somewhere over here and just redo it a bit, because I want these to be essentially just above it. These lines. This to me looks a bit nicer. Okay, let me just move this regulator over here. The same old thing of making sure the distances are right. 2 more. I mean, you don't have to do it as precise as this, so just... Okay. Now, this seems fairly alright, except that we have a ground connection here, and the ground is kind of on the opposite side. VCC has to go all the way around like this. So what I'm going to do is move this diode to make it a tiny bit better. Oops. And then I can move this whole block a bit more like this. And this is more satisfying. So it basically just can come out from this pin and go directly to the right. Yeah, this looks a bit nicer. Okay, so what components are we missing? We are missing the serial wire debug connector, and most of the serial wire debug pins are here, so SWDIO, SW clock, and SWO. And so it makes sense to put our debug connector kind of here. Get rid of the silkscreen. I will move this down a bit more. Okay. Again, I tend to use the 3D viewer just to make sure everything looks kind of alright. I mean, yeah, here it's not entirely the nicest, because here it might be a bit cramped. There's lots of empty space here and here. We could have made the board much smaller, that's the thing. A 5x5 board is far too big for this, but you know, if you want to add more pins, more pin outs, you can do it with this size of board. You can have more connectors on the edges and so forth. Of course, if we take the mounting holes away, this will make the board a lot smaller as well. But for the sake of just, you know, just getting done, because the main point of this video is to just get a working hardware design, which you can then repeat and do your own stuff with, this will do. Okay, so what is this connector? This is just a 3.3 volt. And a ground connector. So I'm just going to put this somewhere here. So this is just so we can measure the voltage or supply external circuitry. I always think it's a good idea just to put an extra power output on the board. Yep. Okay. Now, we have some indicator LEDs left and the pull-up resistors. So let's see the pull-up resistors. So because the trace will be coming out like this, I'm going to be putting one resistor here, approximately, and the other resistor kind of mirrored on the other side. This means the traces can both come out like that and they won't interfere. Yeah, this looks about right. Just let's check the 3D viewer, make sure it doesn't look too messed up. Yeah, that'll do. I mean, as I said before, these aren't too critical. Okay, now we just have essentially the power LED here. Now, I tend to group it with what is actually giving it power, which is this 3.3 volt regulator, so I'll put closer there. And we have the resistor here. Again, check the 3D viewer, make sure it looks kind of pleasing. There's far too much empty space, that's just bothering me a bit, but that is minor. And then of course you have the LED coming out from the microcontroller, just kind of as a status LED, and I'll put it fairly close. Also, what I keep in mind is, because I'm not having the reference designators here, so the Silkscreen which has like U1, U2, R1 and so on, but I will be adding Silkscreen later. So I want to make sure there's enough space for the Silkscreen to be here. So that's what I'm keeping in mind as well. So put it. So you can either put the kind of current limiting resistors for the LEDs directly below or side by side. It depends on how you think the Silkscreen is going to be and so forth. But this basically completes our basic layout. So what we need to do now is actually set up, well, you could do this first, set up the board, how many layers you have, the names of the layers, and the design rules. So the design rules you can check for JLCPCB. If you go to capabilities, you can see, okay, we have dimension tolerance and thicknesses, thickness tolerances, the minimum, this is the stuff where it gets kind of important. So minimum trace width is 3.5 mils, but that's only for, yes, for multi-layer PCB, so we're fine. So for a 4-layer PCB, the minimum width is 3.5 mils, sorry, which is very, very small, and we should not be using that for this one. Again, you want to have as large traces as possible. You don't want to get close to these limits because that will be hard to manufacture. There'll be more manufacturing errors. Okay, but other stuff like minimum spacing, via size, via diameter, via to trace, this is the kind of stuff you go with to KiCad, and you go to the board setup, which is the top left here. First thing we do, we set 4 copper layers. So 4 layers, parts on the front and back. Yep, can just keep that. You can just say 4 layers, parts on the front, which is what we're doing. That's another thing. You kind of want all your parts on the front if you can. It makes it much easier to assemble, to solder. You can put it on the table, and things won't short as much. So generally, parts on the front only is a very good idea. So we've got the front copper. We've got the first inner layer, which is underneath the front copper layer, and that's going to be a power plane. So no traces running on the power plane. The second layer is also going to be a power plane. So, well, the second inner layer. Again, no traces running on this layer. So we only have signals on the front copper and the back copper. We want the inner copper layers to be, this one's going to be ground, the in one, and the second, the third layer, the second inner layer, is going to be 3.3 volts. So you add, I mean, it's only a couple of picofarads of capacitance you add between these two power planes, but it makes sure you have minimum or the shortest return paths possible. You have, you minimize your inductance, and you can always just drop a via down everywhere to get to power. So you don't want any traces running on those. So traces just in front and back. Okay. You can go through all the design rules here, what you want your default text width to be and stuff like that. But these are the design rules which are kind of the most important. So from JLCPCB, you would take this data and fill in these segments here. You can also set default net classes. So for power, you might want a minimum track width of maybe like 0.5 millimeter or something like that. You can do all that stuff here. I tend to, maybe I'm being a bit sloppy with this, but I just tend to create different track widths, and I know for power I want a larger width, and I try to maximize that, so I won't actually give net classes, but that might just be my laziness. This is why I do that. So in tracks, I'll add default widths, so 0.3 millimeters, 0.4, 0.5, and 1 is usually my default widths I go for. So these are all millimeters. For vias, I'll maybe go for 1 millimeter and 0.8 drill as a fairly large via. Okay. And then, oops, yeah, so that's saved as millimeters, the other default units. And you pressed OK. So, but what you should do, I'm being sloppy with this, fill all this data in, because this is what the fab house can do. But I have found that if I just use the default settings in KiCad, these will have much larger gap minimums, so spaces between tracks and track sizes and pad sizes. So it helps me in my design because I stay clear of having very small spacing between tracks. That's the reason I do it. Okay, but yes, so let's start routing. We've set up our layers here, so with the front inner, so the front is going to be signals. This one is going to be ground. This one's going to be 3.3 volts. This one's going to be signals. On the front and back copper layers, I'm also going to be adding ground poles. So why don't we start off with that? An important thing now is we want to essentially fill the whole thing with copper except underneath the crystal oscillator. Now the crystal oscillator needs its own single ground plane, and this ground plane is attached at only one small trace to the rest of the ground plane. We want this as isolated as possible from the rest of the ground. So let's do that. Let's start with the front copper. Our grid, let's make it a bit larger to 1 millimeter. Click on this button, which is Add Filled Zones, and let's just start the top left corner. Now you can go outside of this edge cut layer and click, and then front copper, we want ground, and let's just keep the default. And let's start tracing. There we go, go around the world, like that. Now, we're coming into the area where we need to be a bit more careful. So I will just be going up here, then I'll be going to the right. Again, this is a rough outline. So I want to stay clear of the crystal parts, which includes the pads going into the microcontroller, going around the crystal, closing it off, going here, and then closing the copper pole. Now if I press B, which is fill zone, I can see it's been filled because there aren't any traces here yet, so it's filled pretty much everything except around the crystal, and this is what we want. Now I'm going to change the grid size a bit smaller because I want to keep a bigger clearance. So I'm creating clearance here. So, because otherwise it'll be capacitively coupled as well. So the further your distance between traces and planes, the less capacitive coupling there'll be. Okay. Now we can add a corner by right-clicking. Add another corner, and you see I'm just doing it around essentially all the crystal oscillator parts and also the pads going in the microcontroller. So let's make that a bit larger. Okay. If we press B again, we fill, and we can see, okay, this is looking good. And you see I've only done one plane first, and once I've got the shape I want for this power plane, I can just press Control D, click, and it's been duplicated. And you'll see I have two ground fills here. I need to change one. And then press E to open the options, and just select the second layer. And we want a ground fill on the second layer. Awesome. And then it's filled the inner layer with ground as well. We do the same thing. Select one of the layers, Control D to duplicate, press E to open options. So the inner second layer, we want at 3.3 volts. All right, this is going to be our power plane. And the last one, because we want another, damn it, we want our fourth ground fill to be ground on the bottom copper. Okay, so now we've got the front copper, inner copper which is ground, third copper which is 3.3 volts, and back layer which is ground again. And all of them have the same shape, so they all have this cutout around the crystal oscillator, and this is what we want. Because now we are going to put in the inner layer, so the second layer, we're going to put a little ground fill in here. And that's going to be the local crystal ground. Let's do that. So starting somewhere here, ground, and let's just trace it out. Again, a fairly rough trace, so you see I messed up already a bit. So you can all fix all of this. Okay, so see this is very rough, but of course you can drag it out. Okay, so here, let's change that. go. Make that smaller. So we just want it to just fit on here. I don't know what's done that. Okay. So this looks fairly decent. Let's press B and fill. And you see it's not filled because nothing's connected to this ground fill. Let's just do a design rule check quickly. Because sometimes the copper layers can be too close to each other. So for example, this distance might be too little between the two ground poles. It's the same kind of like trace to trace distance. So the way we can get this ground pole to fill is put a via in. So I select a larger via, click the via button, change my grid because it's snapping. Okay, now double click, change the ground. Now if I press B, okay, just checking that it's actually connected. Okay, now it's filled. Okay, so it had to connect one tracer. So let's do the design rule check again if it's going to complain. Okay, so it's not complaining. So that we have enough space between the ground poles. And you want a continuous ground pole underneath all these connections. Okay, so this via looks a bit big. I think I might use a smaller one. There we go. Now I'm doing the vias which go then down into this copper pole underneath the crystal oscillator. Now, I'm using a fairly large track width, so half a millimeter, and let's connect up the crystal parts. Okay, this looks good. And now, so the pads from the microcontroller are 0.3 millimeters wide, and that's the tracks we always want to use coming out of the microcontroller. So we have the high speed out, and we have this guy. So let's just get it like that. Okay, so this looks pretty good. The only thing I am a bit cautious about, if you look underneath the HSE in, it's not completely, the ground fill is not completely under the high speed oscillator in. So we are going to have to change the copper fills. So I deleted some of them, and I'm just going to make this clearance just a bit more. Also on this side. Okay, let's just mess everything up. Okay, clearance a bit better here. And then I can drag this one up, just so we have a continuous ground plane underneath the crystal traces. I think that makes you a lot happier. Okay, let's just refill, pressing B. Okay, as you see, we don't even need any ground fill around here because there's no ground connections. Okay, so this looks a lot better. So again, that's what we did before, is just duplicate and assign all the layers, 3.3 volts, add copper, awesome, okay. So this is the first part done, which is the most important part for this kind of design, is getting the high speed traces, especially the crystal oscillator traces, just sorted right from the get-go. As you can see here, there's a large cutout, you want fairly short traces, and an isolated ground plane. Okay, let me just, so this is C1, which I forgot to move. Okay, this needs to move over here. Must have grabbed that when I was doing something earlier. Okay, just move that over here. This one up here, perfect. I mean, this is what you're going to have to do probably quite a lot, is just rearrange components as you lay out the PCB. You can't really know everything right from the get-go. Okay, well this looks good. So as I said before, we have an isolated ground plane here, which is not, well, right now it isn't connected to the larger ground plane. And what we want to do is have a fairly small trace just running over at one point into the large ground plane. Yeah, something like this. So the whole crystal ground is connected together, but it's connected to the overall ground just at one small point. And you can see this detailed in several data sheets and application notes and guidelines on crystal oscillators. So this is how I've always been doing it, and it seems to be working. Okay, next thing we do, we go back to our 0.3mm trace width, because we're going to connect all the decoupling capacitors. So because we've placed them nicely, we can just go out immediately. So nice component placement makes the routing easy as well. As of now, all I have to do is just come out like this, drag the traces out. We can even do the boot 1 pins as well. Why not? There we go. This one and this boot 1. Perfect. Okay, so now the decoupling capacitors. So we could just, I mean, there's a ground fill here, but we can just connect over the decoupling capacitors like this. But remember, use the biggest trace size you can. So I'm going up a trace size and connecting everything. It might be easy just to stick with one trace size, but it's much better. It minimizes resistances, capacitors, inductances. So might as well do it. So that's what I'm doing now, connecting everything. Okay. So here we have the LED. Awesome. Okay. This looks fairly decent. Okay, so now we've done pretty much almost the most important part. Another important thing is, of course, the debug connection, but let's do that a bit later. Let's do the power section now. For the power section, power thick traces is what you want. So millimeter should be fine. What can help you check if you go to KiCad, the main window. If you go to the calculator, whoops, where's it gone? Here we go. Track width. Now, if you type in track width, let's say 1mm, trace thickness is about 35 microns, which is thickness. This can carry about 2.4 amps. And yeah, so you can calculate what the current carrying capability is, what the voltage drop will be, and so forth, power loss. So we should be pretty safe with a millimeter. Of course, we can go higher, but it should be fine. Okay, so it's connecting everything up. There we go, and this one. Okay, so that's all the power connected up. Yeah, so let's continue with I2C, which we just drag out. So as you see, the nice component placement means I have a much easier time just routing this. So from this, again, I can move to a bigger track, which is what we want. So one thing I want to bring up is the placement or the spacing between traces. You want kind of as large as possible. If they're not differential pairs, you want the largest possible spacing between them. A good rule of thumb is you want at least a track width, whatever track width you're using. So if you're using 0.5 millimeter here, you want a 0.5 millimeter distance between these two tracks. And, yep, 0.5 millimeter approximately. So this is the kind of rule of thumb you want to go by. Of course, for differential pairs, depending if it's USB, you might have to match impedances, and so forth. But in general, to minimize crosstalk and cross-coupling, a track width between them. So something like this. Now, one thing is a bit annoying with this. If you want to do a track width between them, you're going to get, so if I route this, and then I press B again to fill the plane, you're going to get these kind of disconnects in the copper plane, and you want to keep the copper planes kind of as one piece as you can, so not a lot of these spaces between them. Of course, because this is a 4-layer PCB design, we have this continuous ground plane in the middle. So, for example, here. So it's not really separated, but in general, you don't want to have a lot of these huge gaps between ground planes. It also doesn't look very nice, to be honest. So, yeah. Anyway, let's continue routing. And KiCad will kind of give you suggestions of where you want to put your tracks and so forth, which can be irritating, as now. But if we just follow the guidelines, Okay, now it's complaining because you can't go out there. So this is a case where I have to delete these tracks and then move the decoupling capacitor further right. So take all of them. I hate when it slaps that. Okay, so let's see if I can still get the ground trace. Yep, I can. And this should make my life easier. Okay, so you're going to always have to rearrange components on the go as well. Just do that. There we go. And the last one. Okay, press B to refill the zones. 3D viewer. Looks right, doesn't it? Yeah. Okay. Okay, so the next thing, UART. Refill, always with B, always got my finger on the B key. So we've done the I2C. Here we go. Half a milliliter because this is an LED and a current limiting resistor, so we'll have to display a bit more power. Okay, what else do we have? So essentially the last kind of important higher speed trace is the debug trace. So let's do that. So let's just have a think. So SWO needs to be at the top, so your clock has to go to the bottom, and SWO has to kind of go in the middle. There's no really pretty way of doing this, so let's just go along here. This is a good idea. So SWO needs to go in the middle. Yeah, I think we can we do that? It's not very nice. Okay, let's start with this one first. So the least important out of these three is SWO. So that's why I'm going to be doing that one last. SWO is just the trace if you want to do like, you know, printf via debug and so forth. That's why I'm going to be doing that one last. Let me just see what the neatest way of doing it is. Okay, I'm just going to go along here. Yeah, actually this might be a good idea. So I don't want to go too close to the board edge, but something like this should be fine. And then I can bring, not the prettiest, by all means. So I also want to leave a bit of space here because I'm going to get needing vias to ground. So let me just do this. Here, leaving enough space, of course, again, between the SW clock and SWO lines. Let's B, and let's just check. You see, things like this, I mean, it's personal preference, right? I could make the track separation between these a bit larger so the ground port goes in here. There's no real benefit to doing it other than aesthetics. So I'll just leave it for now. Okay. So now I've got the trace wire coming out here. This is kind of just eyeballing the track widths or separation between them. Okay, I'm going up here. Okay, so I've left some space here because a via will need to go here, which will connect to N reset, the not reset connection, because I can't really get past this upper copper. And N reset is here. Okay, so let's lead that out as far as we can. Here, and press V, then to place a via, or via, however you call it. Now, because we have space here, let's delete that via and actually use a bigger one. Let's use that one. Might as well. Will we be able to fit one there, though, is the question. Yeah, that's fine. So, note on vias and drills, you don't want vias on the Silkscreen because of course you can't print on a hole. So, make sure they're far enough away from Silkscreen so you can still print. So if we do B, 3D viewer, you can see it's just far enough away from the Silkscreen that it shouldn't be a problem. Now the question is, will it be far enough from this trace so it won't throw an error? Yes, okay, so it's far enough from this trace. You want to check again that your vias aren't too close to traces or other vias of different nets, because that'll mess it up. Now because we have these large vias, we can use a larger track on the bottom copper. So we're basically going kind of diglet mode. We're going out on the front copper, going down to the lower copper layer, and then going across and up again. So let's just use one of these. press B to fill the tracks, 3D view, so you can see what we're doing. We're underneath this, we're going on the other side, going along here, and up here into the end reset. So stuff like this. The problem we've created here is that there's this whole ground copper layer here, but there's only very small connections on this side, here and here. It's not ideal. On a 2-layer board, this could be quite problematic. You want to keep these kind of disconnects as short as possible. The thing is, we're using a 4-layer board, so we've got a whole dedicated ground plane anyway, and we can be a bit more relaxed about these kind of things. Okay, so I think we've pretty much got all of the data and signal traces done. What we need to do now is do all the power connections, ground connections. Now, the way we do this is, remember we've got this ground pole and this 3.3 volt pole. Essentially we want to feed from the regulator and from the voltage source into these planes and then distribute it along these planes and use little vias to connect our power and ground pins. So let's do that. So if I use a via here, change my grid. So I'm going to use several vias here. I'll change them all to 3.3 volts. Use even more. And then I will use very thick traces to connect from the regulator Okay, so you can see I have a lot of these, well, not a lot, but quite a few of these vias, then connecting from the regulator into the main power plane. So you can see they're connected here. So you want as many of these as possible to minimize the inductance, because any via will add inductance, and you have inductors in parallel, the inductance will decrease. So you want as many of these as possible. I've had fairly large vias here, so I'm fairly content with leaving it with just these 6. The same thing we have to do for the ground though. So we add more vias, and we add them all around the ground connections. Oops. So we change the net name to ground. So the way I get to that menu is always double click. There we go, ground, ground, and I have loads of these. So ground is probably the most important thing to stitch. So we're going to do via stitching later. We have loads of these vias stitching the different copper areas together. Now if I press B again, you see it's kind of cut out a bit of the 3.3 volt layer because this is our ground vias. Now the problem is you have a lot of these stitching vias. This will also separate different power planes. And so there's kind of a trade-off between how many stitching vias you have and your connectivity of your ground planes and discontinuities. Okay, but let's make sure. Now this should be okay. Okay, and you kind of want to make your vias as big as possible. Smaller vias look kind of nicer to me and are helpful in certain areas where you don't have a lot of space, but for large power traces you want them as big as possible so there's a maximum surface area for the current to flow through. Okay, so now we've kind of done a bit of this stitching. We need to now connect all the other power and ground points. So for every ground point I see here, I would want at least one via which connects to the ground plane. So if I have two 3.3 volt pads here, I want maybe 2 vias going there, and I'll use the small vias now. So I'll have one 3.3 volts, 2 here. So let me just see, I want to fit everything in here, that's the only problem. Okay, let me change my grid size. There we go. And then I also have to connect them up, so I use a 0.5 millimeter track. Okay, so ground here. 3.3 volt here. So my general rule of thumb, as I said before, 1 via per pad. wherever I see it. So rough placement again. So it's basically just via hunting now, or pad hunting rather. Let's connect them up. And of course we'll add more stitching vias later. There we go. Getting there. One more thing is, when you're connecting the decoupling capacitors up to the microcontroller, I could, for example, put a via here, change it to 3.3 volt, and then connect it up, you know, going to that pad. But what I'm doing is I'm going through, connecting it through the decoupling capacitors first to get a bit more of a filtering action. So it's going through the via, from the ground plane, through the via, into the capacitors, and then into the pin. It's a neat little trick, I think. Okay. Yeah, so this will take a bit of time, but it's well worth it. It's well worth doing this properly, because you want to, all areas you can minimize, you have the control over what you want to do. Electronics will oftentimes go wrong. And let's just try and minimize the amount of times we have to pay for new PCBs. Okay, for this one I'm adding quite a few more vias because this is the analog reference. The thing is, of course here we're not using the ADCs or DACs or anything, so in essence this analog voltage pin is a bit useless in this circuit, but you know, nevertheless. So here it's a bit fidgety because we have to stay on the ground pole. So you could, of course, I don't have to connect these ground traces up, because if I try and press B, the ground port does it for me. But the way we've set up the clearances and tolerances on the ground plane, the connections are going to be very thin, and I'm just making them a bit larger by doing this. Okay, so we're actually pretty close to being done with this. So let's connect that, ground. Actually this one, we'll connect more grounds to it because this is at the regulator. Yeah, actually let's use the different wires for this. Vias. I don't know if it's vias or wires. Even if you use them in series like this, it'll still minimize the inductance. Okay. So I'm just duplicating them so I don't always have to reassign the net name. Okay, we have here, these are the pull-up resistors for the I2C lines. We just need one because it's just holding it at a constant voltage. And again, the same old thing of from the power plane through to the capacitor and then into the microcontroller. I think that's pretty neat. Okay, there we go. Have I missed something is the question. Yep, there we go. So of course you can place them maybe better on a grid or something, but it should be fine. Also, here you see I haven't placed a via. I could move these two resistors up and put a via there, but since this is holding the boot 0 pin just at ground, even if there's, it doesn't really matter. It just has to hold at a constant voltage. What I will do is add an extra via here. So let's just make sure, after I've put two of each, that we're not violating any of the design rules. So run DRC. Okay, via to close to via, and where's that? Okay, that makes sense. So I always tend to do a DRC while I'm doing the layout, because otherwise you're going to have probably 100 things come up at the end when you think you're done, and then you have to change everything. So it's better to change everything on the go. Okay. Now we're missing one via here. To be honest, having second thoughts about this via, because this is the VBAT pin, and it is actually not really needed. So let's get rid of that. Okay. Of course, we need this for the debug connector. Okay. So B to fill all zones, run the DLC, and we have nothing unconnected and no problems, no markers, so that's promising. So let's have a look. Yeah, so we've got large views there, all the views going to ground and 3.3 volts, looking good. Okay, this is looking pretty decent so far. The nice thing is we also have a fairly continuous ground plane on the bottom, and we've only used one trace on the bottom, so that's pretty good. So we could say we're done, but if you notice, this doesn't look like very much, and it's kind of empty. So let's add some Silkscreen. It's always good to label everything to say what things are doing what. The way I do it is go to the Silkscreen layer, text, and say, for example, this is I²C. So I'll put it underneath, kind of try and center it, and just about touching here as a reference point. Then I'll duplicate that. We've got SWD over here, make sure it's centered, which it isn't. This is a UART, or USART, doesn't. Okay, what else do we have? We have SPI down here. SPI, and we kind of have a power input, so let's, what should we call that? Just power. Because I'm just thinking, because we have two powers, I'm just wondering what to call this then. Power in, we could call this, let's call it V in. It's not technically right because we have, this is V in and that's the ground V in. It also means we're going to have to move this diode because the Silkscreen is going to be in the way. I mean, in this case it's not too bad, but you don't want to sacrifice. If you have Silkscreen to put somewhere, prioritize the component placement over the Silkscreen. There's no point in making it look pretty if it performs worse. Okay, so let's just say this is then power, let's call it power. Okay, let's just see how that looks. Power, V in, SPI, UART. Okay, yep, looks fine. Now what you could do is also on the top Silkscreen, say this is ground, this is V+, what this pin does, what this pin does, what this pin does. I think for ground it's a good idea just to say, okay, this is negative. Where's another one? This is negative, this is positive. I would always recommend you do that. For this, just to make it look nicer, we're going to put it on the back Silkscreen. So select the back Silkscreen layer, press T for text, and we're just going to put 3v3. Let's put it on the back Silkscreen. Whoops. Sure, it's kind of lined up. So always going to have to play with the grid a bit. Let's see how that looks in the back, if it's the right orientation. So I kind of wanted the other orientation. That looks nice to me. Okay, let's do the same for ground. So of course you can change the font size and if it's italic or not, but okay. I was trying to make sure, you know, I'm using these guiding lines to make sure it's nice and aligned. Let's do A. because I find like a lot of Silkscreen on the top just doesn't make it look very nice, so I tend to only keep the very important things. This will take a little while, but you get the idea. You know, just make sure you label things that are important, not just have the user guessing. VCC, let's call it. What do we have here? That's RX. And then we have TX. Okay. Finally the SPI, and we're almost done. So what's that? That is, I was exclamation mark chip select because it's not chip select. It's inverted logic. And we want to rotate that. Okay, what else do we have? Clock. Okay. So, master in, slave out, and master out, slave in. Okay, let's just check how that looks. RxTX, everything's labeled. Ground, VCC, SPI. Okay. Now, we start to label the diodes. So let's just say power. Let's say power. Let's call it 3v3. So I always tend to look if it's touching or if it's too close to different Silkscreen. Well, this is okay. So just to indicate that 3v3 power is there, and this one was called stat, as in status. See how that looks. Yeah, that'll do. Okay, one last thing for the Silkscreen is indicating polarity and pin 1s. So as you see for the KiCad symbols, it'll actually tell you, you see this side, the Silkscreen here, indicates that that's pin 1. I tend to always put an extra dot next to the first pins though, just to make sure, you know, this is definitely pin 1. Also with this connector, this is pin 1 here, and here it's, I mean, you can't put the component the wrong way around, but you know, someone might try. But polarity for diodes, light emitting diodes, and this diode, let's put that on. And I will do that just by front Silkscreen and just by doing a plus. And just plus as in for the anode. People might not like the plus, but this is the way I do it. And that is always a good thing I think to do. I mean, you have these little, you know, boxes around it to indicate the polarity, but I think this makes it very clear. Okay, let me just add my pin 1 little dot. So I just draw a little circle. It can be very small. It's just to indicate a pin 1, pin 1. Where else could we have a pin 1? There. Remember, don't put it on the VIA. Put it next to it, because it won't print. Is that all we have? We could put it next to the crystal. It doesn't really make a difference, to be honest, because it doesn't matter which way it's installed. But for the sake of just doing it, let's do it. Let's see that they're not masked by any other Silkscreen. Yeah, we can see that. We can see that. We can see that. We can see that. Awesome. Okay. Is there anything left to do? Let's just refill the zones. Check the DRC. And I'm just going to quickly show you how to add a little graphic onto the Silkscreen, because I think that's quite cool. So what you do is open Paint, or if you have a graphic already, let's do that. I'm just going to write some text. What should we call this? Well, STM32. F4 breakout. There's my amazing graphic. Okay. Just make sure it fits nicely. It's the smallest size we can get it. Save that. What do I put that? So let's do Silkscreen logo. Save that as a PNG. Now, go to KiCad, then press this bitmap to component converter. It should load bitmap. Silkscreen logo, port. Okay, now we need to see what size we need. So let's go back to this, and let's see where we want to put it. Somewhere here would probably be good. Let's see what size that is. So Control-Shift-N to measure. It's about 11-12 millimeters by 6. So something like that. So you can change the resolution until you get something like 50x4. We're getting close. Maybe a bit more. There we go. Okay. So this will mean 11 by 4 millimeters, which will fit in the area we just looked at. Now we want it on the front silkscreen. Let's look at the black and white picture because that's what it's going to be exported to. We can change the threshold to 0, of course, won't show anything, and it gets thicker the more you go to 100%. That looks alright. Export. What you need to do is, the new library format for KiCad is create a new folder. Let's do, I don't know, logo silk screens. .pretty is what you need to call the folder for KiCad to recognize that it's a library. And then we just do F4 Silkscreen, let's give it a name, save. Then go to PCB New, Preferences, Manage Footprint Libraries, and add logo silkscreens.pretty. Okay, now we can add footprint. And then let's search for it. What was it? Logo, something like that. Logo silkscreens, there we go. Press OK, and there we go. We have a very little logo. But that'll do. The idea is there. You can make it smaller and larger with that KiCad plugin. Just move it. Where does it look good? Does that look good? Ish. Okay, this is my OCD again. But you get the idea. This means we're basically done. Got all the polarities marked, everything. Okay, so right now it would be a very good idea to just check the whole routing again. Again, check the schematic, make sure everything's correct. Check the data sheets, cross-reference. Of course, for a large project, this is vitally important. So it makes sense to just try it for smaller ones. Yeah, just go through the routing, make sure that the traces look good, all the copper fills look good, you know. Like that. That looks alright. Yeah. Make sure there's enough clearance, so the copper fills aren't like chopped up too much. Okay, it looks good. Now one touch we can do, because we've done all the silkscreen, is add the stitching vias. We'll just add a couple, so I'll just use a small vias, fairly large grid, and let's just go mental. Use a larger grid maybe? Yeah, why not? Okay, so I'm just putting them fairly equally spaced. So you can either do it by hand, or you can then copy the selection, and then just go mental. And remember, you don't want to get this on the silkscreen. So here wouldn't be a good idea because it cuts into the silkscreen, which is a bit annoying, but now, what I'll show you in a second is, this may be great for the ground layer, but look what it does to the 3.3 volt layer. It's really chopped up, and that's not very good. So, while it might look cool, right, this looks pretty, I think it looks cool, you kind of want to go with a larger spacing, because this is completely chopped up, so only current will flow through these little paths here. It's fine for the ground layer, but no, anything else. Whoops, that deleted everything. You might not want that. So, let me just get rid of some of these. Okay, so one there. Again, just always check that it's not cutting your 3.3 volt layout too much. Just make sure they're still on the grid. Okay, this is looking right, I think. You know, you just go on like this. And okay, so I'm almost done. Won't do too much more of this because it's getting rather boring. So just Control D just to duplicate. But this stitching just ensures we have good connectivity between all the ground fills and we minimize our inductance. Okay, so this kind of looks quite cheesy, as they say. Okay, close that. And let's just have a look at it again, just make sure. Looks fairly decent. Yep, for the back, make sure all the vias have got far enough distances. Shape the ground poles. This will be fine. And we could add more 3.3 volt vias, but this will do. Okay, again, run the DRC. Problems marker zeros, unconnected Arduino zeros, and okay, now we're going to get to the part of actually ordering this board. So let's close stuff we don't need. Let's go to our menu. Okay, so I'm going to add a new folder called Gerber, and I'm going to add a new folder called Assembly. I like to separate it out a bit. Then, File, Plot, choose the directory, which will be Gerber, however you pronounce it. Use a relative path, yeah, that's fine. Click on Generate Dual Files, and for JLCPCB, just use these settings. I think they're the standard settings. So plated through hole, non-plated through hole in the same file, absolute dual origin, units of millimeters, and then click Generate Dual File. Close that, and now we need to create the Gerber files for the copper layers, silk layers, and so on. Selected the right ones, edge cuts, which is the outline, front copper, all the copper files, okay, and it's putting it in the Gerber. These settings work, press plot, amazing. Okay, so now we have this here, we're going to have to zip them. So I had to, it can be zip or RAR for JLCPCB, it doesn't matter. I'll just rename it to Gerber. Okay, so now we have the Gerber files which we can upload. Because we want assembly, we're going to have to do a bit more than this. The next thing we have to do is do fabrication outputs and footprint position file. And I'll put this in the assembly folder and include footprint of the SMT pads, single file for board, generate position file. This is going to tell JLCPCB the center of every component and the orientation and which layer it is. So the automatic pick and place machines can just read that and just like, yep, here we go, put these components there. What we also need to do is go to the schematic editor, click the, where is it, BOM, generate materials, and then there's this plugin called BOM CSV grouped by value with footprint. It's in the bin, KiCad bin scripting. It's a Python script. Just click generate, and it will make you a nice little BOM. And that's going to be the main folder. It's going to be a bit hidden. It's this one without an extension. So just do f2.csv and move that to the assembly. Now, double click on the BOM. Just import that. So there's going to be some headers and rows we don't need. So that's what I'm going to delete. Now JLCPCB is a bit particular about the naming of things. So for the reference, we want to call it designator. Quantity, we want to call it quantity. Value is fine. Component name we can delete. footprint we keep, and we delete description, and we delete vendor. Okay, and this is all we need so far, and we need another column LCSC part hashtag, so part number. What I then do is, because Excel and all these programs are annoying, change it to text, and I just change the footprint, so it's 0805, 0603, I'm just making them shorter, 0402, 0402, 0603, 0402, so D123, 0603, 0603, 0805, skip that, skip that. Okay, as you see here, KiCad has also exported the mounting holes. You can delete that, that's not a part. Unfortunately, JLCPCB doesn't provide assembly for through-hole parts and connectors and stuff like that, so we can take that out of the BOM as well. But other than that, now what we need to do is have that open and JLCPCB open. We go to SMT assembly, click the in-stock parts, and now we go through and we need to find all of the part numbers and list them here. So, a bit boring, but we go through 10 microfarad 0805. We choose the basic part, and we copy the part number. Make sure the package is the same. As before, we check the rating. So 10 microfarad 0603. Make sure it's a basic part. Put it in. 100 nanofarad 0603. Is it? No, it's 042, sorry. And 10 nanofarad 0402. So it's the same thing, copy the part number, copy the other. Gets a bit boring, but thankfully this is a short list. 12 picofarad at 402. B581W. Okay, AD Red 0603. Fuse, yeah, the fuse I'm soldering myself, so I'm going to take that out. And then we have a ferrite bead, which is this one here, because it's 100, if you look at the data sheets, it's 100 ohms at 100 megahertz. And the crystal. Okay, so here, copy the part number, but I'm also going to copy the component package and just overwrite this. 2.2 kilo ohm resistor 0603. These are the LED resistors. 10K 042. 1% resistors. These are the boot 0 and boot 1 pull downs. 2.2K 42. These are the I2C pull-ups. And finally, the last resistor is the feed resistor for the crystal. Then we have the regulator. That. Sub 223, they're not including the 3, okay. And finally, we have our centerpiece. And also the package, just copy that. Okay, and JLCPCB should now be able to find that. Awesome. Close that. Let's rename that so we can actually read what it is. BOM. Let's open the position file. Now again, JLCPCB is a bit picky, so we need to change that to designator, as we did in the BOM. Value, package, and this needs to be POSX needs to be changed to mid-X, mid-blank X, and this to mid-blank Y. This needs to be changed to rotation, and this needs to be changed to layer. Now you can leave it, you can take out the stuff we don't need, so this we don't need, connector, well we don't need, they can't place it essentially. Fuse they can't place. Is that it? I think so. Good. Okay, save that. Okay, let's go to JLCPCB. And let's place an order. So just click right now, it'll take you immediately to where you need to be. Add your Gerber file. Desktop, where is it? Breakout, Gerber. Add the zipped file. Wait till that uploads. Almost there. Okay, so now it's recognized it. It's recognized it's 50 by 50 millimeters. It's 4 layers, so it's filled all that in for us. We click on their Gerber viewer just to make sure what they're seeing is what we're seeing. So you can check all the traces, check all the Silkscreen is there. Yeah, that looks alright. You can go on the bottom. Yeah, that all looks fine. Analysis results, they tell you, okay, trace width is larger than what we can do. Perfect. Okay, so we can close that. Now, we have several options. Layers, that's fixed, of course. Dimensions, yep, that's fixed. Quantity, I don't think there's much difference between 5 and 10. Yep, there's no difference. So let's do 5. PCB thickness is 1.6, that's what standard. Impedance, we don't need that. You can use this to do 50 ohm traces and control impedance traces, but for this, of course, we don't need it. PCB color. Now for assembly, they currently only do green, so we're going to have to keep that, and it's also the fastest turnaround. The surface finish, hot air surface leveling, that's the standard, the cheapest. Lead-free might be a good idea. I tend to always go for this immersion nickel gold, I think it's called. It's the gold pads. Look cool, longer shelf life, easier to solder. But for this, let's just stick with the €12 option. Copper weight, yeah, that's fine, that's all fine. Okay, one thing we can change, if you want to, is to remove the order number. So either yes, it'll cost you about 140 more, because it's file of them to track the PCB when it's being fabricated, or we can specify a location. I can just quickly show you how to do that. So you copy this text, JLC, whatever it's called, go back to the PCB new editor, go on, I always turn it on the back because I don't want to see it. Hit Silkscreen, copy that in, and put it somewhere where it's kind of, where you don't want to see it. So you can put it somewhere here, and they'll print the order number there. Of course, I'd have to re-export the Gerber files, but you can. I tend to just press the button, just remove it completely. So that's what I do, remove the order number. Okay, that costs a bit more, but to be fair, not much. Advanced options they've added, don't really need that. But what is interesting now is SMT assembly. Click on that, assemble top side, because all our components on the top side, and that's another reason for doing this, only putting components on the top side. SMT quantity, 5 or 2. You can order 10 or more and they'll assemble 10, but let's just assemble 2. Tooling holes we could have added, which is just essentially in the edge cut layer, making 2 or 3 holes of a 1.152 millimeter diameter. Let's just make them add it. If you're fussy about where they put them, they tend to put them around the edges here somewhere, so it doesn't really matter too much. So let's let them add it. So confirm. Confirm that. Okay. Then you'll get to this step. We have to upload the bill of materials. So in our assembly folder, bill of materials, and the CPL, which is the component placement file, pick and place file, which is the footprint. Let's go next. It's going to scan through it, and here it's going to see, you're going to have to match up and check if what it identified, the automatic system, is correct. So here's what we uploaded, and here's what they think it is. It's 10 nanofarad 0402, 10 farad 0402, 10 microfarad 0805, and so on. You go through and you check everything, and you see everything is a basic part, but there's no extra cost. So you do that, you check everything, and then you click next. Then you'll see if the part placement is correct. So this is where it gets a bit interesting, because JLCPCB is it doesn't take the KiCad files directly without a bit of modification. So you can see in total it only costs about €36 to get 2 PCBs made, and all of that is just a setup fee. So if we're at order 5, the price per board goes down. You can see what parts have been selected, no unselected part, so it's happy with our choice. Now, what it isn't happy with is some of the component placements. You see U1 is rotated by 180 degrees. The pin 1 here is off by 90. The diode seems correct. And the diodes, all the diodes seem correct, but U1 and U2 aren't correct. So what we're going to do is just going to edit in a text file. So what's it? U1 is off by 180, isn't it? So U1, we just add 180 to it, so it makes it 90 to 270. and this one is off by 90 degrees, and the sense of rotation is that, so counterclockwise is positive, so we have to take off 90 degrees, and it wraps around 360, so it's also 270. So we save that, close that, go back, re-upload the footprint position file. Don't have to re-upload the BOM because nothing's changed. Press next, and with any luck, everything's correctly rotated. So U1's correct, U2's correct, all the diodes seem correct, right? That's why I put these dots there. That's why I put the plus symbol there, because I know the anode and cathode of diodes and the part placement. And if you're happy with that, well, all you have to do is press Save to Cart. And you can check out securely. Awesome, and that completes this video. I will, of course, attach all the Gerber files, production files, and so on to this video, and so you can have a play around and hopefully get producing PCBs. If you have any questions, let me know. Other than that, good luck and hope to see you soon. Thanks.